And today we've got Dan Rosen speaking from Uppsala University. And then he's a software engineer in the Pharmaceutical Bioinformatics Research Group. And he's got a background in computer science. And graduated from Göteborg in Sweden. And is now a staff scientist with Jordi and his team in Uppsala. And Dan will talk about the last 3 years of effort in the group and about cell painting, if I understand right. And Dan, you're welcome to share your screen and show us your presentation.
Yep. Okay. Do you see a screen?
Yes.
Do you hear my voice?
Yeah.
Good. Okay. Thank you for this opportunity to have this presentation. So we have a wet lab automation project at Uppsala University in the pharmbio group, led by Jordi, Carreras, Poiver, and Ola Spjut. And we also, our like the software we write for this is also open, and all of it is on this webpage. Now I have a question for you. You see my mouse pointer because I will point at things. I see some people nodding. Okay, good. So I wrote 3 years of the pharmbio robotlab, but it's more like 2 years and 10 months, but it didn't sound as good. So let me just introduce what we do in our lab. And we do, the main thing is a protocol called cell painting, where we prepare cell cultures that are on microplates, small plates like this with wells in them, so you can have cell cultures in them and put different kinds of toxins or compounds on them and see how they react. And what we want to do with these cells is to, which is this painting step, is to prepare them for fluorescent microscopy. This will come back in the presentation. And these two middle things here in the image, we have then a robot arm system for the painting step, which has some cycles where we apply different kinds of chemicals to do this. And then also the image acquisition step, where we image these with a microscope, which is kind of a long process to take images of all these wells. And I will jump over to just show videos of this to get like a better idea of how this looks in practice. So we'll start with the cell painter, and you will see the, okay, just pause. Okay, can you see the video? And one of you? Yeah, you see the video? Good, so this is the our robot arm, plate hotel racks, where we can store many plates, because here is an experiment where we are working on 14 plates at the same time. And we have machines for taking off liquids, it's the washers, and we have a machine to dispense more liquids, the dispenser. And to the right here, you see the user interface, which gives like an overview of the current running process. It's like a Gantt chart, but time goes downwards. And it goes like this. We have an 8-bot gripper, which is a German company that's made this gripper. You can see that. And in the back here, it's hard to, you can't really see it on the video, but what's happening right now is it takes out the plate from an automated incubator with 37 degrees, which is what the cells need while they're still alive. But there is a step where we kill the cells as well. So that's the first system we have. And then the second system, where this is finished and we want to image the plates. We have this system is with an automated fridge, a microscope, a precise flex robot arm, and a plate hotel. On the video, you can also see a Nikon microscope in the background, which we can also use, but in this video, we use the squid microscope. And to the left here, you see the interface. There are two different interfaces running simultaneously here, both the robot system, where you queue up plates for imaging, and then to the left, it's the user interface for the actual microscope. So I'll run here, I'll press start in the video, and the first thing that happens is that a plate comes out of the fridge. And the precise fix arm goes and picks it up, puts it in the plate, and the squid microscope opens, the plate is inserted, and it's closed, and then image acquisition starts. And we start getting these cell images, which is the kind of goal of this whole practice. To have these images and to be able to analyze and to say something about biological effects. That's so I'll just say a little bit more about the different kinds of components that builds this. This is the cell painting protocol, which is like the main topic, where we apply 4 different kinds of chemicals in these 2 different machines. But we will kind of ignore all the details right now for lab automation focus, and just think of it like there are just 5 cycles where we wash and dispense. So we put them in one of the machine, put in the other machine, and then let the plate incubate. And since this is like biological processes or biochemical processes, it's important that we have very little variance in this, so that it always incubates for like 20 minutes, and that there's no variation between the plates. Like we want all the plates to be handled identically. And here I'm doing some calculations, so you can see like how much effort it is to make a batch of cell painting. So this is for 10 plates. Then you have to do a whole bunch of actions. So I just summed them up. There are 40 for the dispenser, 50 for the washer, and in total you have to do about 275 actions. So it's about 2.3 actions per minute. So if you do this as a human, you have 2 very boring hours ahead of you. So that's a good reason why it makes sense to automate this, because it's very agonizing to do. So it's both that and the other that we want to reduce all these kinds of different effects. And then some of these chemicals are also unhealthy, in particular PFA, so it's nice that we don't need to put humans close to these chemicals. And for imaging, it's maybe not so agonizing to have to be like stuck in a room for 2 hours, but it's more about the throughput. So the protocol is just take the plate out from the fridge, wait out 1 hour, because at the bottom of the plate we will have condensation. It looks a bit like the blur in the video. And about after 1 hour you can start imaging. It takes about 3 hours. So if you want to load the microscope like manually with your hand, you can maybe do 2 plates on a work day, and that gives 10 plates per week. And then you always have to remember to do all of this thing with the microscope. And I've written down some things you can get wrong if you do this by hand. And it's not that I mean that our operators are stupid. It's just easy to do mistakes, especially if you have to do something that's kind of boring and distracts you from more interesting things that you want to do. Just like getting the right plate, putting it in the right direction. If you put it like this instead of this, then all the experiment details will be wrong. And then just putting in the right barcode. And then with automation, you can do 6 plates per day without optimization, so like 40 plates per week. And we are using this research microscope called Squid. I've added the link here, and you can also talk to us about it if you want more details. But it's relatively cheap compared to vendored microscopes. So it's also easy to scale it if we would need a higher capacity. We could just use many of them. So just a little summary about like what our automation goals there are. So for the cell painter, just reducing these unwanted lab effects that you will see the effects on the cells, but they are not biologically interesting. So like plate effects that you treat the plate differently. Maybe they're not incubate for as long, or they're just shaken differently or something like this. Or the operator effects, that we have many different operators and they might do things slightly differently, and they can't communicate to each other exactly how to do everything. But here we know that we can run the same thing tomorrow as we did like 1 year ago. And it also makes larger projects feasible, that we can do these templates without our users becoming mad. We have a big screen tomorrow coming up. It will be one of the largest we've done on one single day. It'll be about 40 plates. And I don't think anyone employed here would want to do that manually. And for the imager, we can work it around the clock and also reduce errors. And since we have been running this, so I started then almost 3 years ago, and 2.5 years ago we had the first like automated cell painting, and it has been working successfully. So I think we have achieved these goals. So a bit more about the details of what components build these things. I'll go in detail into them a little bit more, but these are some things that you have to solve to build a system like this. So one is, of course, the machine communication. You have all these different machines that we need to synchronize. So we have a solution with web servers that we can communicate and then make a type-safe Python wrapper. You have to teach the robot arm moves. For this, we also did a custom user interface because we found that the ones provided by the robot arm vendors weren't good enough. And yeah, these moves we can cut up into smaller pieces and aggregate them in different ways. We also need to schedule this whole system, and also schedule and express this protocol in code some way. And this turned out to be not exactly trivial. You can't just greedily allocate this. I'll go into a little bit more in detail how we did that. And then the end user also needs to be able to start the whole the two systems. So we saw before where the user queued up some plates for the imager and pressed start. So we need a user interface like that too. Of course, in the beginning there was just a command line interface, but yeah, our operators weren't very happy to use that. Our robot arm GUI, or graphical user interface to make robot arm moves, looks a bit like this, and then it was first written for this universal robot arm we have, and we also have another kind of robot, the precise flex, so we could port this user interface to also work on that. So in our academic settings, we don't have, I guess no one has an infinite amount of resources, but yeah, we sometimes have to use like secondhand robots, or just robots that we happen to have. So we can't just say, oh, I only want universal robots, or I only want precise flex. We use what we have. And we made it so that each move has 5 steps. You go to some neutral position to the location you want to work with, where you want to pick up the plate. You close the gripper, you move it to where you want it to go, open the gripper, and then go back to neutral. And because you always go back to neutral, you can run these one after each other. And then it sounds like, okay, you need a lot of moves, but not all location pairs are needed in the actual protocols. And a benefit of this is then you can, when you teach the robot these moves, you can make it first go to location 1 to location 2, and then location 2 back to location 1, and just run that in a loop and just see that everything moves smoothly. So one improvement you can do to that is when you have these moves, when you go back to the neutral, say we first need to take the plate from the incubator and then take the lid off. From the incubator, we put it to the kind of neutral hotel, and then go back to a neutral position. But this is a bit unnecessary. if we anyway are going to take the lid off from the plate directly. So we can remove those intermediate moves. And here we don't save. So there's a video of this happening here. Okay, it starts maybe here. It takes the plate from the incubator, which comes soon, then puts it on our kind of neutral hotel position, which is the middle of the top ones here. And then without like going back to a neutral position, it just takes off the lid directly. Okay. This is actually an old video where we have a previous gripper, and we had a lot of issues with this gripper. There's a lot to be said about having a good gripper. Your robot arm is never it's never better than your gripper. Okay, so something about lab robot communications. So what I mean by lab robots is just all these kinds of different devices and machines we have that work on these plates. So automated incubator, fridge, plate washers, and plate dispensers. So I know some of you are into the SILA consortium, which I understand is a uniform and standardized way to communicate with machines like this. And first, yes, we did not know, or at least I did not know about this when I started working on this. So I just made my own way of wrapping all these machines in Python. And I managed to get some properties that I wanted. Like that is easy. I can just use Python decorators. It's like a one-line thing to say, now this is remotable. And also I can kind of fool the type checker. So I use the typed Python version, or a type checker for Python. I can have a remote object which just makes calls, but I can fool the type checker and say it's the machine directly. And I can also add logging in different kinds of way that is uniform for all my machines. So if you compared it with a standardized effort or initiative, I mean, it's a bit different if you're a producer of a lab robot or a consumer. So like we are lab robot consumers in that we use them. And if I have a lab robot and no one has written, or especially if they don't provide a SILA wrapper for them, SILA is not so important for me. But it's more like if you are a lab robot producer, so say you are Biotech, which is the company that produces these machines, and instead of they making up their standard, or like, not their standard, but their method for communication, it would be better if they used a standard. Then maybe someone has written a SILA wrapper for one of these. Like I think maybe there's one for the Lyconic things, but I mean I need to be able to inspect what happens in the communication to these machines in an easy way, and I also need to like be able to debug any issues. So can you trust a fourth-party wrapper which is not provided by that vendor? That could be an issue as well. Trust as in like, is it performing well enough? Also, our developer team is quite small. It is just me, so I don't really need to care about someone else's preferences. But with a bigger team, is of course can be very beneficial to use something that more people know. So yeah, I'm not against SILA. It's just hasn't been relevant for us yet. So that's what I can say. Oh yeah, and to the right here is the right here is the communication that takes place in the cell painter system. So this is one of the two systems. So the machines are on the ends, and this is different kinds of communication channels. So there's a lot of communication happening, and you want to be able to inspect like each edge of these. I just show quickly like how what you get from the wrappers that I made, which maybe can be interesting to compare to like what a Scylla system could give you out of the box. So I can ask the web server what methods it has, and you get it back in hypertext or in JSON. You can ask it to give you a log. I have a simple way with the tail, which I use sometimes when experiments are running just to see what's happening. But for my developer ergonomics, it's quite easy. I just make the methods. I can make a documentation. I add the arguments and their types, and I both get some documentation generated. But the more important things is that I can just access this as web endpoints. And in particular, if I attach them to, I can make an object, which is a remote object which proxies through this HTTP server. But from the type checker, it looks like it's the actual object. So like the thing that is the runtime fridge here, the type checker thinks it is an actual fridge object, but in practice, it goes via the HTTP remote and calls this function. So this is a little bit of code snippets for some objects we have in the code base, a runtime and an execute, which executes commands in a runtime. So then one other big part of this is to just how to express this cell painting protocol in code and how to schedule it. So like on the previous slide where we had a command to be executed, this is also how you express it. You express like a series of commands that you want expressed, but sometimes you have to do several things simultaneously, or you can maybe don't have to, but if you want to cram in as many plates as possible in one batch, which we want, you need to do many things simultaneously. So that's why you have a fork command, which forks a new thread and runs both of them in parallel. And for one thing that made this one command type that I found useful to introduce is like checkpoints and waiting for checkpoints. So instead of just saying I want to be idle for 60 seconds before I continue doing something, I instead first make a checkpoint and then I wait for that checkpoint plus some seconds. And using that mechanism, you can talk about more like long range intervals. Like when a plate is finished in one cycle, you want it to wait for 20 minutes before it can start in the next cycle. You want to be able to talk about 20 minutes plus when the cycle started. Another thing we use here in these plus seconds after the checkpoint, it doesn't need to be like a constantly known time. It can instead be a symbolic time that we will resolve with a theorem prover. And this means that this is our program that we build up to express the protocol or express anything that the robots will do. We can execute them in three ways. It's live, which is when the robots actually do things, where time is real time, and machines execute the things. They perform the action on the plates, and the purpose then is the actual purpose of the whole system. And we can also simulate this, where time is just simulated. It's just you just keep track of how much time has passed in the simulation, and then of course the machines don't do anything. And the purpose of this is testing. And this has been very useful, that before you run an experiment, you simulate the whole program and try to reach all points in the program to just catch bugs. So you run the whole program until you just come to the point where you make the remote call to the machine and you say, oh, it succeeded. And then the third way we kind of execute these programs or work with them is then symbolically, where time is just symbolic. So we just introduce variables to talk about time in relation to each other. And the machines, of course, they don't do anything here. And the purpose of this is to schedule these waits, so we know when everything should happen. And here's an example that illustrates how this can be, or like why this is difficult. And the difficulty is because of a non-linearity that comes from when that you don't know which things will be longest. So here is an example where we have under each step is how many seconds it takes to do them. The pink is the dispenser, the blue is the robot arm movements, and yellow are delays that we need to find out. So in this example, it's simplified, so we just want to wait 2 minutes in the cycle. So after this mito is finished, we want to wait exactly 2 minutes until this PFA starts. And also for this mito to plate number 2's mito. And without going in too much into the details, but if the PFA is shorter, say the PFA is 15 seconds and the mito is 20, then we need to put a delay in the second cycle. But if it's the other way around, if this PFA is longer, the delay instead has to be in the first cycle. So depending on like how these lengths vary, you kind of have to push this delays in various parts of the program. And this happens non-linearly then, because you have like a discrete bump where you start putting delays in one area instead of another. But you can do this, you can express this and solve it and schedule tens of plates using this mechanism. And this is just as an illustration with time going downwards of how it looks when you schedule 4 plates. One thing that I can also mention here is you can also interleave these steps. So the plate starts in incubation, then goes to B21, which is the neutral hotel position, then to the washer, then to the dispenser, back and back to the incubator. So if you want to make it simple, then you just take one plate and go through these machines and back again. Then start with second plate. But you can also try to interleave this in different ways. And the way I found it easiest to experiment with different kinds of interleavings, as I call them, is to just write them in this kind of ASCII art. So this means that the first plate goes from the incubator into the washer, and while it's being worked at in the washer, which takes like 1 or 2 minutes, the second plate gets out from the incubator and waits in this neutral position. When the washer is finished, you can put that in the dispenser, and take the neutral plate and put that in the washer. Now both the washer and dispenser is running, and when the dispenser is done, you can take that out and put that back into the incubator. And then this is just for 3 plates, and you can expand that algorithmically to many plates. So this is not found by a solver, this is found by me beforehand. So depending on these cycles, it can be different machines involved. The interleavings look slightly different depending on the machines in question. So just pick those that work best. And one thing I want to say here about this these choices of automation. Just want to like slightly higher level talk about what our problems are in terms of choices and how complex then the scheduling is. So for the imager and for the painter, you can make all your choices statically, like you know exactly what you want the plates to be exposed to, or like what you want them to do. If you contrast this to maybe something like cell culturing, which is something we don't automate, but we might in the future, the choices become more dynamic in that you have your plate in the incubator. Maybe you wouldn't have you might have a 6-well plate, but same idea. You take it out of the incubator and cells are growing in there, and you want to see how many cells there are. And depending then on how many cells that are alive and are dead, maybe you want to throw them away, or you want to split them into many wells, or you just want to keep waiting. So that's more of a dynamic choice. And we, in our two systems, we haven't had to deal with dynamic choices. And then the scheduling for the imager, you could do just like a linear or greedy scheduling, which just do steps after each other. But for the painter, that's when we have this non-linear, tricky delay situation to meet all these deadlines for incubation. And then for cell culturing, I don't really know. It might be feasible to just use like a linear or greedy scheduling, or you might actually need to do something more complicated. I guess a whole other automation axis is like how the spatial geometry of your lab looks like. So we assume that everything is static in space, but like if you are working on autonomous driving, then also space would be dynamic, that things move around. That's an axis that we don't have to care about. And I think now I just want to summarize a little bit. So we introduced our lab where we do cell painting and microscopy imaging, and it has some nice benefits. Then we can increase throughput for the microscope, or just the amount of batch or the size of the batches we can work with, and without making our operators agonized. And we can reduce these kinds of just errors and lab effects. We discussed a bit about the CELA and the lab robots. Wrapping needs to be uniform and inspectable. It's important that you can troubleshoot. Sometimes this can be, it has happened while experiments should just start, or when it is running, you want to know quickly what has failed. And one thing that has been important is that we can simulate these software easily. So we have had many issues in our labs with the robots or the machines, but so far I don't think we have had to cancel any experiment because of software errors. And then scheduling can be non-linear even if you just have static choice. That's what I just talked about, that even if you know upfront everything you want to do with your items, like our plates, scheduling can still be tricky. But everything we made is open source, and you can look at that and be inspired if you want to use something from there. And you can contact me by email, or if you just want to say something, you can also just post an issue on the GitHub tracker. And this is our research group's webpage, pharmbio. That's that.
Perfect. Thank you very much, Dan. Very impressive talk. And you shouldn't need to feel you have to apologize for not using Zila. So
okay.
The thing is, if this works for you, it's absolutely fine. And I know myself, if you're the only one working automation, there's just no way it's just too much work to do everything perfect. You just do it the way it works, and then you keep improving. So, but yeah, I guess Well, I will stop the video first.